We have another day on integration by parts, and the truth is that the problems that we're about to do are more involved and more complex than the ones that we did yesterday. Fortunately, we've only got 2 videos worth of stuff today, and we're going to do fewer problems, so we're going to get a chance to focus on them a little bit more. I call these problems circular problems because they feel like they're just going to go on forever, and there's a trick that's going to let us sort of like break out of that, and so you'll see that as we get into these examples. So here's my first one. This is sort of a classic problem. By the way, these circular problems almost always look like this. There's an e to the x and there's a sine x. There are some other ways they can show up, but generally speaking, it's an e to the x and it's a sine or a cosine. Like like 90% of the time, that's what they look like. Okay? We're going to do integration by parts on this. I'm going to choose my u to be e to the x. I'm going to choose my dv as sine x dx, right? So I'd like you to pause the video, work through integration by parts on that. Just do one step of it, just get it transformed, and then we'll regroup. Your du is e to the x dx. Your v is negative cosine x. Yeah, negative cosine x. So then we rewrite this thing. It becomes negative e to the x cosine x minus the integral of e to the x cosine x dx. There's actually another negative here, isn't there? Yep, so that's plus. Okay, so great, we did it, right? Now, unfortunately, you're looking at this thing going like, man, I don't know how to do this. This looks like it's probably going to require, an integration by parts again. So let's do it again. When you do it again, don't, like up here, we committed to e to the x being our u and the trig thing being our dv. Don't switch that back around. If you start here going, oh, this time let's make our u cosine x, it's actually kind of funny. It'll just undo the work you just did, which is bad. So let's not do that. Stay the course. Choose your u to be e to the x. Choose your dv to be cosine x dx. So again, if you're feeling up to it, pause the video and compute your du and your v. We should get du being e to the x dx. V is sine x. So then again, we rewrite the integral portion of this thing. So the negative e to the x cosine x sticks. The rest of that thing becomes plus uv, that's e to the x sine x, minus the integral of v du, that's e to the x sine x dx. And at this point I'm supposed to pause for dramatic effect, right? I'm supposed to pause for you to take a minute to sort of recognize how depressing the situation seems to be. What's depressing about this? What's depressing is the problem started out as the integral of e to the x sine x dx. We then did 2 integration by parts methods, and now I have the same stupid integral again. Like, I did all this work, and I feel like we've come around the circle. I call these problems circular integration because I just did that stuff, and I'm exactly back where I started, which is totally annoying. Fortunately, it's also totally amazing because of what we're going to do next. Right? Think about what I can do now. And you sort of have to bear with me for a second. I think I'm going to have to zoom out a little bit. This problem is therefore equal to the integral of e to the x sine x dx. So what can I do? I could just add this integral over to the other side. Because they are exactly the same, I can add it over, and when I add it over, I get 2 of those integrals equals negative e to the x cosine x plus e to the x sine x. Now all I have to do is divide the 2 over. When I divide the 2 over, I'll find out that the integral that I wanted to get all along is equal to, 1/2 times that. So I'm going to sort of do some factoring at the same time. E to the x over 2 times negative cosine x plus sine x. In my opinion, one of the hardest things about these problems is remembering that you still need plus c. And there is no formal place where that really showed up, but because it's an integral, I need plus c, and that's it. Okay, so the way these circular problems work is you do integration by parts twice usually. Once you've done it twice, or you do it until your integral looks like what you started with, add that integral over. In this case, there were two of them. Why were there two? Well, there was one of them here and one of them here. If in the course of, like, suppose this had been like 5 integral, great. When you add that 5 over, you're going to end up with 6 of those integrals. Divide that number over, and you're done. I would like us to have us look at one more of these problems. I'm hoping it'll go a little bit quicker. Before you start the problem on your own, let me start everybody going in the right direction. We need to choose something as our u, and we need to choose something as our dv. With circular problems, it doesn't actually matter which one you choose, but I want us all to be on the same page, and there might be a better choice, right? Is it better for me to put my e to the 2x in this position or in this position? My opinion is that it's better to put it here, because the product, or not the product, the chain rule is going to give us like a 2 in this derivative, whereas if we put this thing here, we'd end up with a 1/2, and I'd rather not deal with fractions. So I'm going to put my e to the 2x here, and I'm going to put my cosine x dx here. So everybody should be able to, do the first step by doing integration by parts. I would say do that step and then unpause and make sure you got to that step with me, then pause again and sort of do the second parts by yourself. So I've got 2e to the 2x dx. Your v over here is sine x. So when we rewrite this, we've got uv, that's e to the 2x sine x, minus the integral of v du, that's 2 e to the 2x sine x dx. So again, pause the video here and work through what the next substitution is going to be, what the next parts is going to be. My u is now 2e to the 2x. My dv is now sine x dx. So my du is 4e to the 2x, and my v is negative cosine x. So now we'll substitute that thing in. I have e to the 2x sine x minus, and then I'm going to put all this stuff in brackets here, right? Minus uv, negative 2e to the 2x cosine x, minus the integral of v du, which is negative 4e to the 2x cosine x dx. Okay, and so now we have to play really carefully with our negatives, right? These negatives are going to cancel each other out. Then this blue negative here gets distributed in. Right, so we'll sort of carefully write this stuff down. E to the 2x sine x plus 2e to the 2x cosine x minus 4 integral of e to the 2x cosine x dx. Okay, now, did we come full circle? I think we did. If we zoom out a little bit, we can see it better. Sure enough, this problem originally was about the integral of e to the 2x cosine x, and that's what I have here. My integral here is equal to the integral I started with. Sorry for the mess there. I can now take this integral, the negative 4 of them, and add them over. When I add them over, what I end up with is 5 of those integrals equals what? Basically equal to the stuff here that wasn't a part of that integral. So equals e to the 2x sine x plus 2e to the 2x cosine x. Last thing we do is we divide this 5 over to this side. And when I do that, I also kind of factor at the same time. These problems very commonly have that e factor that's ready to come out. So when I do that, I end up with e to the 2x over 5 times sine x plus 2 cosine x And of course, don't forget your plus C. Okay. So we went through 2 examples of circular problems using integration by parts. It is possible to do these problems using tabular integration, and I'm going to show you how to do that next. I don't know if it's a shortcut or not. Like, some people in the past have preferred to just do 2 integration by parts. Some people prefer tabular integration. So we'll see it come up next, and you can choose for yourself.